Hey guys, welcome to Chapter 4, 4-3, Day 2, Conditional Probability, and the tricky at least one probability. I think conditional probability really isn't that bad, but for some reason students have a hard time with it. So hopefully with us being able to talk about it in class together, it won't be so bad. Okay guys, this review sheet is actually online. You can go ahead and print it out if you want. That way you can have it in class. And this is already online as well. And this is online also. It's just no longer due the 3rd. It's now due on Friday, and that's November 8th. And then there's also a 4-3 quiz that I squeezed into there, and it's also due on the 10th as well. Okay, nearing the end of the chapter, so let's start looking for that test on the 12th. Okay, so again, this is what we're doing today. It's a super tricky day. You may want to watch this video again after we go through the classwork, just to really solidify all of the concepts in the video. Okay, conditional probability. This means the probability for the second event B should take into account the fact that the first event A has already occurred. So what's going to happen is I'm going to use the word given when it comes to conditional probabilities. I'll say, find the probability of B given A has happened. So that's what I mean by conditional probability. There's a condition involved. So the word given is going to be in the actual problem itself. So this is the formula. Again, with all of these probabilities, you really don't need a formula. Sometimes the formulas muddle things up and make it a little bit more complicated than it needs to be. But the intuitive approach, which I talk about in the next slide, is a little bit easier. But just in case we want to do the formula method. So probability of A is all the ways that A could happen. All ways A can happen. And then the probability of your numerator is going to be all the ways B happens along with A. You'll understand when we get to an example. So the probability of B given A, that's what that little side means, is given. So probability of B given A would be using that formula right here. The probability of A and B occurring together over the total probability of A. Okay, this is the intuitive approach. These two little points down here are really good to use. So the denominator is going to consist of all of the outcomes of event A. So you're going to look at only event A. You're not going to look at anything else but event A. So this is going to actually eliminate a lot of numbers that are going to be in our tables. As soon as you do that, then in event A, you're going to have a separation. There's going to be, several different things. You've been talking about pregnant, not pregnant, positive test result, negative test result. Well, if I said find the probability of a negative test result given she was pregnant, this would be an example of a conditional probability. All you care about are the pregnant people, because you know the girl was pregnant. So you're going to look at the pregnant people only, and then of those pregnant people, you're going to zero in on the negative test results. So that's how you're going to work through this problem. Okay, so here's an example that I was just saying. Find the probability that the person tested negative. That's absolutely hilarious that I did the exact same thing. I really didn't know that. That's funny. Find the probability that the person tested negative given that she was pregnant. So how I do these problems is I start at the end of the sentence. So given that she was pregnant means I'm going to completely ignore these two numbers. Why do I pick those two numbers? Because those two numbers represent not pregnant. And what do I know? I know that this person was pregnant. So I can eliminate those two. This just became my denominator, so I always write that on the bottom. 80 plus 5 is what I tell kids to do. Write that on the bottom. Now, one of these numbers is going to be my numerator. It just depends on which one represents the negative. So I go and look up here. This is positive, this is negative, so this becomes my numerator. So I have 5 over 80 plus 5, which I get 5 over 85, and that is equal to 1, or actually what we're going to start doing here is probably decimals. So let's go ahead and get in the habit of it, 0.06. But either one, the reduced version of that or the decimal would be correct. All right, let's try the next one. Find the probability that she tested positive given that she was not pregnant. All right, so I'm going to go through and I'm going to erase all these little markings because no longer do I need those. How cool is that little trick? All right, now I'm going to be writing in blue. So given that she was not pregnant means I'm going to go up here at the not pregnant and I'm going to use those numbers. So which two numbers do I not care about? I don't care about those because they represent the pregnant people. And I know for a fact that this person was not pregnant because it was given to me. So what's the probability that she tested positive? So I'll get, well, real fast. If she's not pregnant, what are my denominator numbers? 3 plus 11 would be my denominators. And remember, one of those numbers represents my numerator. I just need to determine which one represents the positive. So that would be 3. So I do 3 over 14, and that would reduce down to 0.214. Okay, remember we round decimals to 3 decimal places, and we simplify fractions all the way to the reduced form. Okay, here's a you try. Go ahead, it's a very similar problem. Remember what we're going to do, given that she was female, means I'm going to ignore a certain row of numbers. So go through and figure out which row of numbers I'm going to ignore, and of the 2 numbers that are left, I want to know the one that answered yes. So try to do my method of the denominator being 2 separate numbers that we're adding, and then the numerator being one of those numbers. Sometimes that helps kids out. Okay, go ahead and pause the video and try the problem. Okay, so here are my answers. I got 2 over 25, which if you wanted to put it in decimal form, you would have gotten 0.16, same thing. 3 over 10, which if you wanted to put it in decimal form, you would have gotten 0.3. So either one is fine. You can put either answer. All right, good job. If you have any questions, make sure you put little question marks by them so I know to go over that with you tomorrow in class. Okay, guys, take a big breath because this is where it starts getting to be little thinkers. So the complements, the probability of at least 1. So at least 1 is equivalent to 1 or more. That means at least 1, at least 2, at least 3, at least 4, at least 5, ... at least all of them. That's what at least 1 means. So it would be challenging to find the probability of at least 1. It would be really hard. So we don't find the probability of at least 1. We actually find its complement. And remember what we did by complement. We did 1 minus the probability of the complement. So that's what we're going to be finding, and that's sometimes what's tricky, is finding that complement. So here we go. Here's this little part. The complement of getting at least 1 item is that you get no items of that type. So this is what I think down here. I do think of this from time to time because I have a difficult time with at least 1. So think about it this way. If it asks at least 1, that is the same thing as finding the probability of 1, probability of 2, probability of 3, all the way up to the probability of all of them. So what is the one occurrence we did not talk about? We didn't talk about none of them. And that's why we do that's why we use none of them to find the probability of all of them, of at least 1. Because if I do 1 minus none, remember what all the probabilities add up to? They all add up to 1. So if I do 1 minus that one occurrence that we're not talking about, that would leave all the probabilities for all the other ones. So that's what we're going to be doing today. All right, so here it is again. To find the probability of at least 1 of something, calculate the probability of none, then subtract that result from 1. So you can do this simply by doing this right here. The probability of at least one equals 1 minus the probability of none. There is a tricky little one that talks about, it's kind of like a double negative, the probability of at least not 1. So the probability of at least not 1 would be all R, because again, remember, at least not 1 means at least not 2, at least not 3, at least not 4, at least not 5, all the way up to at least not all of them. Not working, not whatever the other words mean. So what's the one occurrence that we didn't talk about? At least, all are. That was the one occurrence we didn't talk about. Okay, so I know this is going to be a little foggy, but we're definitely going to clean it up tomorrow in class. Okay, so let's just first talk about finding the complements of stuff. So finding the complement of at least one girl. So that would be at least one girl, at least two girls, at least three girls, at least four girls, ... all girls. What's the one occurrence I didn't talk about that happened right before this one? No girls. Those would be complements. Okay, what about no traffic violation? I would have no traffic violations, and then the complete opposite. Think about it up here. No girls, and the complement was at least one girl. So no traffic violation. The complement of that would be at least one traffic violation. Okay, at least one alarm clock works. So at least one works, at least two works, at least three works, all the way up into at least all of them work, right? All work. So what's the one thing we didn't talk about? None work. Good job. At least one alarm clock doesn't work. So this is what I was talking about in the previous slide with them not. So at least one alarm clock doesn't, at least two alarm clock doesn't, at least three alarm clock doesn't, all the way up into at least all alarm clocks don't work. So what's the one occurrence we talked about? All clocks work. Good job if you're able to get those two. Those last two are a little confusing, a little tricky. Okay, so here's a probability problem. The thing is, you've done this exact problem several times. So a couple wants to have 3 children, and they want to have at least one girl. Figure out the probability of at least one girl. And I know what you're thinking. You could go do the whole list of them, BBB, BBG, ... all the way to GGG. And you know that at least one girl means from here all the way down. So we know that there's 7 occurrences out of a total of 8. So you were able to do this problem the very first day of the notes. What I'm going to show you is just a different way to do the problem. That's all. So I like to set up my notes this way, doing these 3 questions. What's the probability of getting a girl? Getting a girl. What's the probability of not getting a girl is what we fill in here. Now you're going to change this with every problem. And then how many times? What I mean by that is how many times are we picking here? We're picking 3 kids because we have 3 children. So we're picking 3 kids. Okay, so ask yourself, what's the probability of getting a girl? 1/2. What's the probability of not getting a girl? That'd be getting a boy. 1/2. And then how many times we're going to be doing it? 3 times. So here I always write down, after I do all that, I write down my probability of at least one girl. And I have to think about its complement. So its complement's got to go over here. So the probability of at least one girl, at least 2 girls, at least 3 girls. What's the one thing I didn't talk about? The probability of no girls. So of not getting girls. That would be this probability here. And I know it's the same, so it's a little tricky this time around, but it's just the pattern. It's just the thought process I want you to getting into. So the probability of no girls, that would represent this probability. So I would do 1 minus 1/2. And where the 3 comes into play is that's what you're going to raise your actual probability or your fraction to. So 1 minus 1/2 to the third. So that would be 1 minus 1/8, which is equal to 7/8. So there's your answer. Matches what we figured out the very first day of this class. We're going to do a bunch of these right now, so let's keep practicing. Okay, example 3B. A game is played by drawing 4 cards. So right there, down here, you automatically know you're doing 4 cards. That's going to be our exponent at the very end of it all. That is our exponent. And from a deck and replacing each of them. So if we were replacing each of them after it is drawn, that's going to change it from when we don't replace it. So find the probability of at least 1 ace. So we're talking about getting an ace. So what's the probability of getting an ace? That's what goes here. So getting an ace versus the probability of not getting an ace. So that's what goes there. So I have to think about, okay, go back to the very beginning of probability. What's the probability of getting an ace? Well, I have 4 aces in the deck out of a total of 52 cards. So that would reduce to 1 out of 13. I have 1 out of 13 chance of getting an ace when I pick it out of the deck of cards. What's the probability of not getting an ace? Well, there are 48 total cards out of 52, and that would reduce to 12 over 13. Now what I need to do, I need to go and make sense of at least 1 ace. So here I'm going to do probability of at least 1 ace is equal to 1 minus the probability of what would go in as a complement. So at least 1 ace, at least 2 ace, at least 3 ace, at least all of them are aces. The one thing I didn't talk about is no aces, or none. And I'm going to raise that to the 4th power because I'm picking 4 of them. So 1 minus the probability of which one of these represents no aces? That one. So I would do 12 over 13 to the 4th power. And that is equal to 0.2739, which if I'm going to 3 decimal places, that's right there. That makes me round that up to a 4. So my answer would be 0.274. So that would be the probability of at least 1 ace is drawn from 4 cards. How would the problem be different if it was without replacement? So without replacement, I wouldn't be able to come in and do this step right here. I would actually have to go through and take apart a card every single time. So here, what I'm going to do, I'm going to leave it as 48 over 52 this time because it makes a little bit more sense instead of reducing it to 12 over 13. And you'll see what I mean. So again, we're doing the probability of at least 1 ace is equal to 1 minus the probability of no aces. Right, and I can't raise it to the 4th power this time because I don't have the same number to the 4th. I'm not raising the same number. My probability is going to change each time because it's without replacement. So I'm picking 4 cards. So the probability of no aces, the very first time around, how many cards do I have that are not aces would be 48 out of a total of 52. I'm picking another card, so I'm multiplying. And now I drew that card was a non-ace, so it's out of the deck. So how many cards do I have left that are non-aces? 47 over 51 because that card is now gone. That card's now gone. I'm drawing a 3rd card, so I'm multiplying. It's a different event. It's a different trial. I now only have 46 cards left in the deck that are not aces times 50. And last but not least, I'm doing it one more time again because I had 4 cards. So 45 over 49. Oops, sorry, that was really ugly. 49. And again, this has to be 1 minus all this. So I would put that all into your calculator, and when you do that, you get 0.281. which, as you can see, 0.274 and 0.281 are extremely close. So we can tell that without replacement and with replacement really doesn't make much a difference for this specific problem. What I have squeezed down here at the very end, as you can see, I can't see because it's blocking my recording, but right here, don't confuse this problem with getting all aces. If I ask you to find the probability of getting all aces, as soon as I use that word all or none, then it becomes a very simple probability. You don't have to worry about doing 1 minus. Getting all aces is simply just 4 over 52 raised to the 4th, and of course that is with replacement because our denominator is staying the same. If it was without replacement, then I would have exactly what I have right above here. Without replacement is right up there. Okie dokie. But without replacement, and that would be not getting all aces. So that would be not getting all aces without replacement. So I have 48 cards that are non-aces, 47, 46, 45. That's without replacement. Okie dokie. All right, so here's a U-try for you guys. I want you to go through, try this problem out, the probability of having a bow tie or buying a bow tie versus the probability of not buying a bow tie. So as you can see, I have it right here as 3%. Before we even go on, I wouldn't put 3% down here. Remember, we needed to make this into a decimal, which would be 0.03. So make sure you guys are putting that one down. All right, I want to do 4 customers, so that's how many times, and I'm going to let you guys try to work out the rest of this problem. So go ahead and pause the video and try it on your own. Okay, there we go. The probability of a bow tie would be 0.03. The probability of not a bow tie, how did I get 0.97? 1 minus 0.03. That gives me his complement, 0.97. How many times am I picking? I'm picking 4 times. So find the probability of at least 1 minus p of none to the 4th power. So none would be 0.97, and we raise that to the 4th power. Okay, and the probability of you picking the same customer twice is very small. So that's why we don't worry about the independent versus dependent. Because what a lot of kids do here, and they just completely mess this up, they put 97 over 100, and they times that by 96 over 99. Don't do that. Don't ever do that. If I give you a percent like this, you're never going to assume it's with, you're always going to assume it's with replacement. Because the probability that you're going to ask the same person twice in the same day is extremely small. We don't worry about that. So don't worry about it when we come to these problems. Don't ever do this. Please don't let me see this on any tests. I'll put a sad face next to it if I see that. Okay, so you guys go ahead and try this problem again. And it's another you try. See if you can figure out at least one doesn't find a job and at least one does find a job on his or her chosen field. So go ahead and pause the video and you try the problem. Okay, there you go. So the probability of them getting a job is 0.48. The probability of them not getting a job, we do 1 minus 0.48, and that gives us 0.52. We're picking 5 kids. So at least one doesn't would be the same thing of at least one doesn't, at least 2 doesn't, 3 doesn't, 4 doesn't, at least all 5 don't find a job. So what's the one occurrence we didn't talk about? That one at the very beginning. They all find a job. So that's what I have right here. What's the probability of all of them finding a job? And which of these 2 probabilities represents all finding a job? 0.48. So I put 0.48 in there. 1 minus 0.48 for the 5th gives me 0.975. Right below it, at least one does find a job. That would be 1 does, 2 does, 3 does, 4 does, all 5 does. That means the one thing we didn't talk about is none. So that's why we have 1 minus the probability of none to the 5th power. So none would be represented by 0.52, and so he goes into there to the 5th power, and then we get our answer. Okay, there's one more you try. So go ahead and try this problem out and see if you can figure it. And pause the video and try it on your own, please. Okay guys, this one's a little bit trickier because it's got the whole multiple choice question thrown in there. So you have a random guesses for 5 multiple choice questions. So that 5 is what goes down here for how many times are you going to be doing multiple choice. You're going to be doing it 5 times. Find the probability that there's at least one correct answer if there are 4 choices for each problem. This helps me out with the probability of each of these little things. The probability of getting it right, well, there's only one answer out of a total of 4 choices. That's what this means right here. And then the probability of getting it, of not getting it right. So this would be basically of getting it wrong, is what I should wrote here. Right? What I should have written there. But the probability of not getting it wrong, that kind of, it's like a double negative kind of thing. Sorry to make that confusing. So the probability of at least 1 correct would be 1 correct, 2 correct, 3 correct, 5 or 4 correct, which means all of them are correct. What's the one thing we didn't talk about? None of them being correct, which would be represented by that probability. So we do 1 minus 0.75 to the 5th, and then we get 0.763. All right, you guys, good job. You made it through one of the challenging videos. I'm super proud of you. Thank you so much for watching, and I'll see you in class tomorrow.